Hi, this is a tutorial of Lie groups for robotics. I will explain Lie groups not by delving directly into mathematics and then trying to solve problems, but the other way around. So I will go directly into the problems and then I will apply Lie groups to solve them. I will also attach code to it, so there will be a repository which has this URL where those two problems are also resolved in code using PyPose. Okay, so the first problem will be pose interpolation. So in the problem of pose interpolation, you have two input frames. One is the initial frame that is represented by TWI, so the initial frame in world coordinates, so how the world sees the initial frame. And then the other is the final frame, and we represent it with this transformation. That is how the world sees the final frame. The output is one or more. In this case, you can see two in interpolated poses, so poses that are between the initial and the final. In this case, we have the pose 1, represented by the transformation TW1, and the pose 2, represented by the transformation TW2. There could be more, there could be just one. The important thing is that are intermediate poses between the first and the last. The second problem that we will resolve is pose averaging. In pose averaging, say that at t-1, so the previous time step, we have an estimate as the previous pose, which will be t-1, this one. We will utilize this transformation, tw to t-1. So how the world sees the previous pose, t-1. And then we will assume that we have different sensors. We will assume that we have inertial sensors that will provide us this frame O. Then we'll have a camera that will provide this frame C. So let's say that we have very expensive 3D camera and we get this frame. And then we have some maybe foundational geometric models and provides us this AI frame. Note that all these sensors provide transformations with respect to the previous frame. Okay, so the previous frame was t-1. The current frames are those here. So the idea is that the real or good or optimal estimate of those frames will be something in between. So we will just average those. Okay, there is the possibility to do weighted average, which is in the code, but now I will explain just the average for the sake of simplicity. And by averaging those, we will get this thing here. Okay, and we'll assume that this is the current frame. And note that this is represented from the transformation of t-1 to t. Okay, so as previously I said that I would not go into mathematics and then try to solve the problems, but there should be a very basic, at least baseline. This is not explaining mathematics of transformations, but this is just making sure we are all in the same place and we all understand the same when we mention transformation. So it is clear. Okay, so I will explain the SC3 group, but this is more a review of something you should already know. Okay, so let's say we have a frame I, and let's say we have a frame F, and we want to see how the frame I sees the origin of the frame F. Okay, so for that we will use this transformation, so transformation from I to F, which means how I sees F. And for this tutorial, I will use mostly the representation of the 4x4 projective matrices, but in principle for all the Lie groups is representation agnostic. So all the operations that we'll show in the future has its own implementations in regards to the implementation of the SE3 group, which implementation of SE3 group is called usually representation. Okay, so you can have quaternions plus transformations, translations. You can have dual quaternions, but we will use this as the representation. Okay, so you want to get P, which is this vector. We just input the 0 position, so it's 0, 0, 0, 1. This is the 0 position of F, and will provide us this 0 position seen by I, which is this P. And if we would like to do the same for this axis, which we'll assume this axis is the x-axis, then we will introduce it here. This is just 1, 0, 0, 0. Okay, and this will provide V, okay, which is this. Okay, so this thing will go to here, and then V will project onto the basis of the frame I. Okay, this is something you should know, and just for the sake of making sure that we are on the same page, I just explain this. Same for the very basics of transformations. TII means you are doing nothing. How I sees itself. How does a frame see itself? Well, this is the identity matrix. The inverse has always exists and has a closed form. This closed form you should already know. For rotation is the transpose, and then for the translation is the negated of the rotation transpose plus the translation. Okay. Then in regards to inverse, the inverse is switching off frames. Okay. So if you have the transformation as to how I sees K, and you want to invert this basically transformation that signals how K sees I. Okay. And there should be the chaining. Okay. TIK composed by TKM is TIN. Okay, this is type of what is a group, because a group has a group operator, which actually is here is the matrix multiplication in the case of the 4x4 matrix multiplication. Basically also has an inverse, so this should exist, and has a neutral element. Okay, top of that is manifold, etc. But I will not delve into mathematics. This is just a review of the very basics you should be comfortable with in order to understand this tutorial. Okay, so let's delve directly into the pose interpolation. As I said, we have an initial pose, a final pose. This is the input. The output, in this case, we will assume we only want 2 intermediate poses, but we could choose just to have 1 or have 3 or have 5, whatever we want. Okay, in this case, there will be 2. Okay. So what do we do here? Well, we do what something you should already know how to do. Is the first thing we will do is remove the world frame. But because what we want is have the frame 0, so the initial frame sees the frame 3. Okay, so if we have this transformation of 0 to 3, which is this transformation, the one that moves from here to here, those interpolated transformations will be partial transformation, not the complete thing, but just a chunk of it, okay, a piece of it. This would be 1/3, and this will be 2/3 of this large transformation, okay? So we will need to know T03. Okay, so what is T03? This you should know, but this is quite obvious. Is transformation from 0 to world, and then composed by the transformation of world to 3, which is the last one. Okay, this we have here. Okay, and this we don't, but this is the switching these indices, so we invert it. Okay, so this is how 0 sees 3. Okay, so we have T03. This is the whole transformation from here to here. So we need to take a chunk, as I said, right? So how do we take a chunk? So this is the idea. We would like to take 1/3 of it or 2/3 of it, but we cannot. Okay. In this transformation, we cannot take a 4x4 representation, projected representation of SC3 and just divide it by 3, because what we would do is go outside the manifold. So we no longer have an orthonormal matrix. The elements are just totally corrupted. Okay. But the idea is this. Okay. So I put between quotes just to signal that this is the idea, although mathematically we cannot do that. Okay. So how do we do it? So we do it by using Lie algebras. So what are Lie algebras? Well, Lie algebras we will label in using this V thing. So transformations, which are elements of the SC3 group, will be capital T. And Lie algebras, we will call them V. Okay, so for the transformation from 0 to 3 will be V03. And we will apply the logarithm, this function, the logarithm, to move this transformation to the Lie algebra. Also note that we have this weird symbol. We will call it V because it has the shape of a V. That I will not explain. I might explain it in a later video, but you should assume that whenever you have a transformation and you apply logarithm, you will also apply this V. Okay? And then you will have this vector. What is this vector? Well, this vector is something that falls under R6 and has 3 linear velocities and 3 angular velocities. Okay, and note one thing that is quite odd is that we are doing a mapping, and this will be actually one-to-one mapping, because then the reverse, we will reverse this with the exponential that we'll explain later on. So it's this one-to-one mapping is mixing things, right? Because this R basically comes from rotating angles, so comes from angles. You can use Euler angles or you can use other representations, but at the end of the day are 3 angles. Okay, so you have 3 angles that represent R, but here we are using radians per second. We are not using angles, we are using angular velocities. The same for the transformation. Here, this is a transformation in meters, but here you cannot see meters, you see meters per second. So this is linear velocities. Okay, so this is mixing apples and oranges, and we need to understand how those are tied together, because if you don't understand how they are related, then you cannot interpret the Lie algebras and you cannot interpret the Lie groups and how they are connected together. Okay. Okay, for that, I will tell a story. So in the beginning, at time equals 0 seconds, we are the identity. Okay, so this is what happens in the beginning. Then we move at constant velocity. Okay, so we will move only at constant velocity, and we will use the Lie algebra. This is V03. So the output of the logarithm is the constant velocity at which we will move. And for how long? 1 second. We will move 1 second at the Lie algebra constant velocity. And if we do that, this identity will be converted or transformed into T03. Okay? So this is the idea. In the beginning, we are the identity. We move at constant velocity using the Lie algebra. We do that for just a second, and we end up in the transformation that is the input of the logarithm. Okay, this is how they are related to each other. What is the advantage of the Lie algebra? The advantage of the Lie algebra is that now we can do these divisions. You remember before we have these double quotes here, because this was the idea, but we couldn't do it mathematically. Now we can do it mathematically. We can divide it by 3 and we can multiply it by 2/3. And here would be like multiply by 1/3. Okay, this is a vector space. And remember, vector space is closed under the scalar multiplication. Okay, so this is valid and this is correct. So what do we do to get the transformations? As I said, there will be the inverse of the logarithm, which will be the exponential, okay? So the exponential, you place this v01 and then this sort of Mexican hat, which is the inverse of the v. And by doing that, you get the transformation. Okay, so we are reversing the process of the logarithm, but now we have v01 and v02. So now we have these transformations, okay? We recover the transformations. So as now we have these transformations, we can represent them in a world frame. So how the world is one, it's just this transformation, which came in the input as a representation of the initial frame, multiplied by or composed, if we think more in group theory, by T01, and the same for the second frame. Okay? Good. So let's now delve a bit deeper into the Lie algebra. As I said, this is a bit of an odd thing that we are using velocities here, linear and angular velocities, and here we use radians and meters. So I explained this story that we start at time 0 with the identity, we move at constant speed using this Lie algebra, and we end up here. Good. So let's try to delve deeper and try to understand them better. For that, we will dissect the Lie algebra. So we will start with the angular velocities. Okay, the angular velocities are the easiest to understand. So with those angular velocities are related only to the rotation matrix, or in the representation when you have translation and quaternion, that would be the quaternion. Okay, but translation plays no role here. This is important. Okay. So, and what does this mean? Well, this says it's radians per second, but let's think about it. We are rotating using this constant angular velocity for a second. So what does this mean? This is a almost primary school problem. Okay, so if I rotate at this angular velocity during 1 second, obviously this is what I will rotate. This is the total angles I will rotate. So despite this be radians per second in the more purest form, this would be also radians, okay? Just because we do that in a constant velocity for a second. So there you go. So these are the radians of rotation around Wx, Wy, and Wz, okay? And then note one thing. If we would have the axis of rotation, and we would want to know how many radians it rotates around the axis of rotation, we can just take the norm of this chunk of the Lie algebra and will provide it to us. Okay? And then obviously the axis of rotation is nothing but this vector normalized. So you normalize this vector, you get the axis of rotation. You compute the length of this vector, and you know the radians around this axis of rotation. Have you analyzed each component of this vector, and you know around each axis the radians it rotates, okay? And you would say, well, this is like Euler angles. No, this is not Euler angles. And it's very important. Euler angles are all entangled one into the other, okay? So it's a chain of rotations. Those axes are totally independent, okay? So you don't have gimbal lock. There is no gimbal lock here. those axes are independent. It's necessary to be independent, because if they were not independent, they would not form a vector space. So this is a vector space. This means that each one of those is independent and you don't have gimbal lock. It's very intuitive. In the user interface, you can draw this as an axis in 3D, and this is very informative, very nice, and sort of closely related to quaternion. So if you want to transform this into quaternion, it's pretty easy. Okay, so let's go now with the linear velocities, which are the things that are a bit strange when you start using the logarithm in your Lie groups library, and you try to understand what it generates, and it's not intuitive. Okay, and this is related to what the group does. Okay, so this is not a failure of the Lie algebras and Lie groups. It's just signaling how it behaves. Okay, so linear velocities. Okay, so what it depends, the linear velocity, it's not only depending on this translation, it's also the rotation. Okay, rotation will drive also this. Okay, oftentimes, well, this will be equal to this if the rotation is the identity. Okay, only in that case. Well, there could be, but this is the main case. Okay, so the linear velocities depend on R and this translation. And how comes this happens? Well, this happens because the SE3 group, which is the main group we are analyzing, is the semi-product between the SO3, which is rotation, and T3, which is the translation. Okay, what does this semi-product mean? Well, this semi-product means something very easy and commonsensical. So say you have a robotic arm, and the robotic arm, the end effector, is in a position and in an orientation, right? So if you translate the base of the robotic arm, you can translate the position of the end effector, but not the angle. The angle you won't be able to, the orientation of the end effector, you will not be able to change it. Okay? But if you rotate the base of the robotic arm, or if you move any axis of the robotic arm that will change the angle, chances are, not always, but it can happen, that the translation and the orientation changes. So basically, you made the translation, you change the translation to change the orientation. Whenever you move an axis in a robotic arm, chances are you do both. What does it mean? This means that when you change something in the rotation space, you may not only change the rotation, but also the translation. Okay? And this is the idea, intuitive idea of the semi-product. Okay, let's put an example. Let's say that we have this in SE2, so this simple group into D, Vx, Vy, and Wz. Okay, so 1, 0, and minus P divided by 2 as this angular velocity. So we said that the this angular velocity will be actually the radians we will rotate. So we will rotate clockwise 90 degrees. So we start here at t equals to 0. And then after 1 second, we should be here. Okay? And let's analyze this linear velocity. So we move towards this axis and we rotate this direction. Okay? So we move forward here and we rotate, we will end up here. Okay? So the translation is 0.64, this, and minus 0.64, this. Okay? And this thing is different from this thing. Okay? Just because we have this rotation that distorts the translation. Okay? This is important. And let's analyze the transformation. Transformation, as I said, depends on an angle. In this case, just 1 because it's into D. And this is the translation. Okay? And this, you can observe that it's different from 1, 0. Okay, this is important because if you have a transformation and you apply the logarithm, and then you analyze the linear velocities, and the linear velocities are different from your translation, this shouldn't shock you. Okay, this is normal. And then we'll go for the silly case. So the silly case is we don't have angular velocity, so it's 0. We only move in x at 1 meter per second, so we end up at 1 meter. And in this case, yes, it's correct, right? The translation 1, 0, which is in this matrix, is the same as the velocities. Why? Because this WZ is 0, the angular velocity is 0, okay? This is important as well. Okay, so let's review a bit more the exponential map. So you have this x, you have this linear algebra, you add the Mexican hat, and then you get the transformation, okay? Then what is the reverse? So the logarithm of this will provide this, which is the same as this. Okay, so this is kind of a circular thing. Okay, you do the logarithm and then you can revert with the exponential and vice versa. Okay, important thing, the exponential of the 0. This you will see a lot, especially in machine learning, because you are interested in 0 vectors in the Lie algebra very often, because this means you reconstruct transformation. So you will see 0 when, for example, odometry maxes a loop closure. Okay, so what does it mean, 0? It means 0 is that you did nothing. You didn't move and you didn't spin, so you did nothing. And what does it mean that you did nothing? The identity, okay? You will generate the identity matrix because the identity matrix means you did nothing. And this is the compact form that all the good implementations of the groups and the algebras must obey. Okay, this is a very good thing you should add into a unit test. You can sample the algebras, exponentiate them, and check if they generate the transformation that we're generating from it. So basically, what you can do as well is take a URDF or robotic arm, uniformly, not necessarily uniformly generate Lie algebras, but uniformly generate thetas of the different angles of the axis of the robotic arm. This will give you a transformation. Then you do the logarithm of this transformation and then the exponential of this transformation, and you should recover t. Okay, so load the URDF, uniformly sample thetas, take the transformation, do the logarithm, and then the exponential. And then the question, do I regenerate the transformation? If it's yes all the time, then it's a good implementation. Otherwise, there is a bug in your implementation, okay? Then nothing. Let's say that we want to utilize Lie groups, Lie algebras, and this is tied to the example that I showed of the exponential of the 0. Okay, so let's say that we want to optimize beta and lambda. Okay, this can be the intrinsics, extrinsics, some refinement of whatever you want of the sensors. It doesn't matter, beta and lambda. I want to map this map F to fit this T star. Okay, so we have a data set on beta and lambda and T star, which is our target transformation. I want to map this F. This F, let's say it's a neural network. So this neural network will take those guys and try to fit this. Okay, if we wanted to do that without Lie groups and Lie algebras, the problem is this needs to generate a transformation. Transformation have some restrictions. We don't want restrictions because they are very complicated. So we want something simple and easy. Okay, so what do we do? Well, we can make the F to generate Lie algebras, because if this generates the Lie algebra, we are not constrained. We can generate anything in R6. So we can just make it spit out 6 units, okay, without any activation function. And that's pretty much it. It will work, right? Because the only thing you need to do is to add the exponential. The exponential in PyPose and other good libraries will preserve gradients. This Mexican hat preserves gradients, and it's quite kind of easy and simple, actually. And then you compose it with the inverse of T star, which is your target, okay? So what should you expect? Well, if F does great, this should be the identity, right? Because if this does perfect, this will be T star. So T star inverse composed with T star is the identity, right? And if it does sort of not okay, it will be not the identity, but not very far from the identity. And I will now explain what do I mean with not very far from, okay? But let's finish this thing, okay? So here we get the transformation, which in the optimal case will be 0. And then we do the logarithm, okay? Why? Because if we utilize this as a loss function, right, we need a scalar, right? The scalar, what will be? Well, will be a number. And the norm of the logarithm will give you the right scalar to backpropagate your gradients in on-manifold optimization, right? Because this will be, for example, 0 in the case that F does perfect. And then the zero vector, the norm of the zero vector will be the scalar 0, so nothing will be backpropagated, right? And note this, and this is very important. The concept that is very important is that the norm of the Lie algebra is the length of the geodesic on the manifold. And what does this nonsense mean? That means that what I said, if it does sort of okay-ish, this should provide a larger number than 0. If it does bad, it should provide a number that is larger. And if this does dreadful, this should provide a very, very, very large number, okay? So the idea is that these Lie algebras, the Lie algebras and the length of the Lie algebras are a very good indicator as to the distance of this transformation that is inside, right? This is a very important property. For the practical case, you might weight it because you might be more interested in the angular error or the translation error. And sometimes translation errors will be very large in kilometers, and if you measure them in meters, will be very large, and basically you will ignore the angle. So you have to, most of the times you will weight it in, say, small robots like the UR5, like Universal Robot. You may not weight it, and you may apply directly this, okay? Otherwise, you would weight it. Good. So this is kind of introduction to on-manifold optimization and how you would apply the algebras in your, for example, PyTorch code to optimize neural networks. Okay, so now that we are well equipped and we know better, let's do things wrong. Let's do things wrong, and for that we will basically do the interpolation, but we will make a mistake in the post-interpolation. And we will do that on purpose to learn more about the algebras, to learn more about the groups, and also to review all the things that we already explained, right? Because it's for a tool to be used properly, for you to know how to use a tool, you should know when to use it and you should know when not to use it, okay? So we covered the when to use it, but we didn't cover the when not to use it, okay? So now it's time to do that, okay? So we have the initial frame, the final frame, and the intermediates that we want as out, okay? As I said previously, if you remember, we wanted the T03, and then we made chunks of the T03, by converting to the logarithm and then multiply by 1/3 and 2/3, okay? But you are used to using Laplace transforms and Fourier transforms, and what you usually do is you transform into the Laplace domain or the Fourier domain, you do mathematics there, and then you do the inverse Laplace transform and the inverse Fourier transform, right? And you think, okay, the same dynamic might apply here. I can first do this, apply the logarithm, work in the logarithm, because it's very easy, very straightforward, because it's a vector space, so what could be easier than that? And then we do the exponential when we get the result, and we are done. So we basically, the logarithm transform into easy maths, then we do the computation on easy maths, and then we do the exponential, and we are done. This will not work, right? But let's try to see how it doesn't work, okay? So first we do this. We transform everything into Lie algebras, okay? So in this case, what we want to do is transform into easy maths, and then we will work with those Lie algebras, okay? So VW0 and VW3 from TW0 and TW3, okay? So we don't remove the world frame, we keep it. Okay, so then what do we do? Well, we want the V03 because we need to do chunks, right? But it's easy because basically the V03 is just the subtraction of those, okay? I put here a question mark because this is a very good question mark, right? Because this will be not necessarily true. So in some cases it's true, in some cases it's not true. I will already advance for commutative groups, it is true. For non-commutatives, it's not true. Okay, but this is the mistake we will assume, we will make, okay? Because we will assume this is true in all the cases, okay? Even in the case that is not true, it can be an approximation, okay? But for now, we're just going to assume this is potentially true, okay? So what do we do? Well, we have V03 and V03. Basically from here we can construct V01 and V02, okay? And we can do even this more generic, like V0i, and we multiply by I, and we divide by 3, okay? And then we take this and we move into the exponential, and we get the transformation from 0 to I, okay? As I said, this should not work, okay? And the mistake was here. Okay, so what's going on here? Okay, so let's analyze what we did previously when it worked and what we are doing now that doesn't work. Okay, so the problem stems from the V03, right? This is the problematic guy. So the V03 is the logarithm of the transformation of T03. Okay, this is correct. There is no problem. And let's wait a second. What is T03? Well, T03 is TW0 inverse composed by TW3. Okay, this how 0 says 3. Okay, nice. But we know a lot about Lie groups and the algebras now, and let's go and let's delve deeper and let's decompose those. Okay, what is the exponential of those? Okay, so this is e of the minus, because let's remember there is an inverse here, VW0 composed by e of VW3. Okay, so far this is totally correct. Okay, see, we just decompose it, and this was what we used to get the right and correct solution. But now, with our new approach, what we did is assume that this is actually this. And what is this? Well, this abstraction is just taking those exponents and moving them down. Okay? So you can see an x here. X means basically it's not equal. But why is not equal? How comes it's not equal? What is the signal that here should tell us that this doesn't make any sense. Even if you don't know, Lie groups and Lie algebra, you should kind of perceive that something is really off here. Why? Okay, so we are saying that this is equal to this, sort of speak, right? Because it's the sort of internal. So there is a mapping, a one-to-one mapping, and we say that this is not the same, but this is equivalent. This is equivalent to this, and this is equivalent to this. There is an equivalence, okay? There is a bijection of the elements, and this is a bijection of the operations. And what doesn't make any sense? Remember, here there is an operation, which is the matrix multiplication, which is the group composition, and this composition is non-commutative. You cannot take this guy and move it here, okay, or take this guy and move it here. It's the same. You cannot do that, right? Those don't commute. This operation that is here doesn't commute. And what is this arithmetic that we are doing here? Because this is a minus and there is a plus here, right? Well, those commute because it's a subtraction. I can move this here and it's valid, and I can move this here behind and it's valid. It is correct. So we are saying that there is a one-to-one representation of a non-commutative operation and a commutative operation. And this doesn't make any sense, okay? And those three guys who studied this very well gives us how this works, okay? Usually this is called BCH, okay? So basically in a compact form, the logarithm of e to the x and e to the y is x plus y plus 1/2 of x, y, and those brackets. This is basically the commutator, plus here is a chaining of commutators. So commutators and commutators, this goes into like a convoluted chain of intertwined, let's say it like that, is intertwining the commutations, okay? And this should sound you familiar, because this looks a lot like how you would do a Taylor expansion by linearizing a nonlinear function, okay, or any function. Good. So anyways, what does this mean? This means that if you want to do this logarithm, you have a linear approximation that is x plus y, okay, but the whole thing has a lot of non-linearities. These are the non-linearities of the manifold in Lie groups, okay? And the non-linearities are driven by how it commutes, okay? So let's say that we would use the group T2 or T3, which is the translations. This would be actually correct because translation don't commute, okay? Just if you don't do any rotation, you just translate, you don't commute. It's a pure, fully commutative group. So this commutator will give us 0, because basically this commutator says how much x and y non-commute. Okay, so if they totally commute, this is a 0, and this is correct, right? And this is actually how you would do interpolation. When you do interpolation, say in primary or secondary school, if you do something silly in Python, that you want to interpolate one point with another point, you do this, right? So you have just one line. So this silly interpolation, obviously you can do this subtraction. The final position minus the initial position, then you divide by the steps, and then you stack them up and you form a line, okay? But in general, when you have interesting Lie groups, like the SE3 that we are dealing with, which is non-commutative, this is not true, okay? But nonetheless, this is actually also an approximation, right? And we will see later on that, like you would do with a lot of robotics, that you get actually the Jacobian and things along those lines, that you get linear approximations and you iterate on those linear approximations, and this works out to do something that is nonlinear. But for here, for this post-interpolation, we don't do that. We do the correct way to do it, okay? Which we can do it, which is using this, right? We don't do this. This we don't do, okay? Nice. So now we are in the next problem, which is the post-averaging. So what is post-averaging? Post-averaging, basically, you are at t minus 1, so the previous time step. And in the previous time step, you have an estimate of the transformation seen by the world frame, tw to t minus 1. Okay? Then you utilize the sensors that you have in your robot to try to estimate where you are at time t, which is where you are. So the inertial sensor will provide you this frame. So from t minus 1 to O will give you this transformation. You have very expensive 3D camera will give us how we move from t minus 1 to also t. So that will be the C for the camera. And then a very VGT or depth anything, correcting for scaling, that is important. And will provide us this transformation and this frame, okay? Now that we utilized all the sensors, what we need to do, or one thing we could do potentially, if the frames are different, chances are they are different, is doing the average, because we don't know if this is the right one, or this, okay? So we will average them out, and I will do the simple average. We can do potentially weighted average, but I will not explain it. Although in the code I did implement weighted average. And this average will be this frame here, okay? And this frame here is from t minus 1 to t, okay? And we'll assume that we are exactly here, okay? So basically, the post-averaging can be used, for example, to detect how we move given the sensors we are providing, okay? Good. So how we resolve this? Let's go step by step. First, we take the Lie algebras of these transformations. Okay, from t minus 1 to these inertial sensors, from t minus 1 to C, the camera, t minus 1 to A, which will be the AI, and we take the Lie algebra. So we start with the Lie algebras. To be noted that those are small transformations. We are assuming that here we are sampling at a decent frequency rate, and we don't move a lot. We move a tiny bit, okay? So those are the Lie algebras. Good. So what do we do then? Well, we are in the Lie algebra world. So in the Lie algebra world, we can do arithmetic because we are in the vector space. Okay, so we can just add them up and divide them by 3, okay? And this will give us Vt minus 1 t star. Okay, there is a star, and the star is literally the star of this lesson, okay? So why did I say t star and not t? Okay, this is extremely important. Well, it is not t because of what we said before, right? We said before that what we cannot do is precisely do this. And we are here doing precisely this, okay? So what we are doing is saying that the average of those in the Lie algebra space is the same as the average if we would use the proper transformations, okay? And this is just factually not true. But it is not exactly totally not true. It is an approximation, and it is a linear approximation, okay? So long we are not very far off, and we are in more or less a reasonable range, we can assume that we are not going to get very far off from t, okay? So that is why we use t star, because here we know we are not in t, but in t star, but we know t star will be not very far off because we just took a linear approximation, okay? Good. Now we do the exponential and we take the transformation. Now what do we do with the transformation? Well, what we do with the transformation is basically try to get new transformations with respect to this new frame. And why do we do that? Well, we are converging, okay? So we are doing an iterative algorithm where this t star is closer to t. So we are closer to the solution. So let's start here. So this is our new starting point is t star, which is very close to t. And we are going to do exactly the same, but now we are much closer to t. What does it mean? That if we do the linear approximation, it will work even better because it's less nonlinear because we are closer. We are less far off. Okay? So we do the same. We take the Lie algebras and we do the average. And this, let's notice from t star to t star star. So t star will be close to t, and t star star will be very, very, very close to t. Okay? And we say that we stop there, okay? Because we already converged. So how does this look like? Okay, so we have this blue thing, which was the pose at time t minus 1. Then as candidates for t, we have this for inertial, this for the 3D camera, and this for the AI. Okay, what is the first step? Well, we get this Lie algebras, we do the average, the exponential, and we get t star. T star still will not be t because we know by BCH that what we did is not proper, but as we know that those transformations are not very far off, well, we will make some mistake, some error, but not much, okay? So we are getting a bit close to t. And then we start from here, so we get this transformation, and this transformation. We do the logarithm, we do the averaging, and we get this transformation. So from t star to t star star and t star star, it's already very, very, very close, okay? So we can assume we stop here and we assume t star star is a good approximation of t, okay? So we go step by step, okay? This is done in robotics all the time. You have EKF and other algorithm where you all the time say, okay, I linearize here, I iterate, and by iterating it works, and graph slam works the same way. So this is no surprise here, okay? So just to be more accurate here, basically we'll assume that this transformation from t minus 1 to t is approximate t minus 1 to t star. Note that we did 2 iterations, but you can do as many as you want. And in actuality, in the code, you can choose the iterations you make, okay? Usually you will stop when you see that you more or less already converge, okay? And what is this thing? Well, it's the first iteration composed by the second iteration, okay? Because those collapse, and you get t minus 1 and t star star. Okay, and that's how you solve the problem, okay? Note that here there are even more mathematical details that I didn't mention. For example, the NSE3, I think it is called left invariant. It's not the by invariant. So I think you left multiply by some Jacobian to get their convergence, etc., which you don't necessarily need to do for rotations because rotations are by invariant. But those are a bit more complicated things, and it's enough complication for that, okay? Also, bear in mind that sometimes you will not have the t minus 1, right? So you will have 3 poses, and you need to average them out. So if you don't have t minus 1 and you have those 3, what do? Right? So one thing you can do to average them out is say, average the translations, do the logarithm of the rotations, average them out, create a transformation of those, and this is a good initial seed. Okay, a good initial seed. Simply when you have those and you need to do averaging, you try to get a good frame that is close enough so that when you run the iterative algorithm, you get there quickly. Okay, you can get the identity and you use the identity, but if those are very large, especially in translation, it may do ill effect. So it's better to do some quick, dirty approximation so that you get some reference frame that is not very far, and then you do this transformation from this frame that is not very far to those. Okay, and if you do that, then you know that these linear approximations are very likely to converge as you iterate. Okay, just watch out with this. And then a last thing that can be a bit confusing is say that you are given a transformation from t-1 to t, which is what we computed in the previous one, and you are asked to know what are the velocities. Okay, and this is very commonsensical, probably you already know, but just to make sure that you don't get confused by this tutorial. Obviously, you will use the logarithm because the logarithm gives you velocities, and this velocity is the velocity of the robot, yes or no? Obviously, this is not the velocity of the robot, right? Because this Lie algebra comes from this story that you move from the identity to this in 1 second, but you don't move in 1 second, you move in delta t. And this is the implementation. Your robot will have its own delta t, which is of your choice, okay? So basically, the real velocity is the logarithm divided by the delta t that you have, okay? Well, that's it. There might be other things I could comment on, but I think it is enough for now.